In this video, we are going to talk about a free particle moving in the x direction. Free particle in x direction, okay, or free particle in one dimension. That is what we are going to discuss about. Okay, let us consider that we have a microscopic particle, and this particle is moving in the x direction. Means that this particle can move along this axis, the x-axis, okay. And what are the limits of this movement? Actually, there is no limit to this movement. It can move to positive x direction to negative x direction. If it is moving to this direction, it can move as long as it wants. So it can move up to negative infinity. And when it is moving to this area, it can move up to positive infinity. It means that there is no boundary for the movement of this particle in the x direction. So it can move from minus infinity to plus infinity. And it can move in either direction, either to the positive direction or to the negative direction. And this is a free particle. Free particle means it is not confined to any other external force. It means that it's a potential energy. Potential energy V is equal to 0. Okay, so this particle is not under the influence of any other external force, and this particle is moving in the x direction. And since it is not under the influence of any external force, it will keep on its movement in the x direction. So it can move either in the positive x direction or negative x direction. How much it can move? There is no limit for that. It can move from minus infinity to plus infinity. That is what the free particle in one dimension, or we are considering the free particle in the x direction. Okay, so we are going to quantum mechanically treat this particle, this microscopic particle. How we are going to treat a quantum mechanical? How we are going to treat a particle quantum mechanically? What we are doing, the general procedure is we are going to set up the Schrodinger wave equation. So whenever you are treating some system quantum mechanically, what you are going to do is you are going to set up the Schrodinger wave equation for that system. And from that Schrodinger wave equation, you will derive the wave function and also the energy. Okay, so what is Schrodinger wave equation? Schrodinger wave equation is h cap psi is equal to E psi, where h cap is the Hamiltonian operator, psi is the wave function, E is the energy of the system, and psi again is the wave function. So let us now set up the Schrodinger equation by expanding the Hamiltonian. Okay, so here psi represents the state of this system. Okay, or psi is the wave function of this system. So the Hamiltonian is minus h square divided by 8 pi square m d square by dx square plus v. This is the kinetic energy part of the Hamiltonian, and this is the potential energy part of the Hamiltonian. Since in our case, it is a free particle, v is equal to 0, therefore our Hamiltonian reduces to h cap is equal to minus h square divided by 8 pi square m d square by dx square. Okay. So with this Hamiltonian, we can set up the Schrodinger wave equation for the system. So the Schrodinger wave equation for the free particle is h cap psi means minus h square divided by 8 pi square m d square by dx square of psi is equal to E psi, right? That is a Schrodinger wave equation where E is the energy of the system. Okay, and now let me rearrange this equation. D square psi by dx square is equal to minus 8 pi square m e divided by h square into psi. Okay, I can write like this. I just cross multiplied this 8 pi square into the numerator of this one, and then h square has come to the denominator here on the right hand side. Okay, So that's all. So let me write it again like d square psi by dx square is equal to k square psi. No, sorry, minus of k square psi, where k square is equal to 8 pi square me divided by h square. Okay, k square is 8 pi square me by h. So let me put that in a square so that we will take that again and we will take this again. Okay, this is very important. K square is equal to 8 pi square me by h square. So if I am rearranging this equation further, I can write it like d square psi by dx square, sorry, plus k square psi is equal to 0. Okay, so this is a second order differential equation, and the general solution of the second order differential of this type is psi is equal to, okay, so this is in the standard format now. So the general solution of this one is psi is equal to a sine kx plus b cos kx. Okay, that's the general solution of this equation. And here a and b are arbitrary constants. This one and this one are constants, and we have k also here. And here, this wave function will be a well-behaved wave function for all values of a, b, and k. So there is no limit for the values of a, b, and k. Okay, or in other words, a, b, and k can assume any value. And now we have a solution for the Schrodinger wave equation. The solution is psi is equal to a sin kx plus b cos kx. Okay, and even if this is a solution, okay, we cannot draw enough information from this one. I will tell you what is it. Actually, this appears like a sine wave, okay, or sinusoidal wave, but it is difficult to draw the information related to the wavelength of that wave, okay, from this one. So what I am going to do is I am going to conveniently convert this expression to another type of expression. Okay, I am not going to change anything, but I just make it in I just transform it into a convenient form. That's all. For that, I am going to use a trigonometric relation. Perhaps you already know this, that e raised to plus or minus I kx is equal to cos kx plus or minus I sin kx. You know this relation. E raised to plus or minus I kx is equal to cos kx plus or minus I sin kx. It means that e raised to I kx is equal to cos kx plus I sin kx, and e raised to minus I kx is equal to cos kx minus I sin kx. Okay, so from this one, now let me do some mathematical steps. Okay, e raised to I kx plus e raised to minus I kx, okay, divided by 2. Let me calculate what is this. E raised to I kx plus e raised to minus I kx, that is equal to cos kx plus I sin kx, okay, plus e raised to minus I kx is cos kx minus I sin kx divided by 2, that is equal to 2 cos kx, okay, because cos kx plus cos kx, but I sin kx and minus I sin kx, okay, this will be cancelled. Okay, so we have 2 cos kx divided by 2 that is equal to cos kx. So e raised to I kx plus e raised to minus I kx divided by 2 is equal to cos kx. Okay, keep that in mind. Now I am going to calculate e raised to I kx minus e raised to minus I kx divided by 2I. That is what I am going to calculate now. That is equal to cos kx plus I sin kx plus, so not plus, minus. Okay, we have to give minus now. Okay, minus e raised to minus ikx. This is e raised to minus ikx. So minus e raised to minus ikx, that is equal to minus cos kx plus I sin kx. I sin kx divided by 2i divided by 2i. That is equal to cos kx minus cos kx. This will be cancelled. Cos kx and minus cos kx, right? And what is remaining is I sin kx plus I sin kx. That is equal to 2i sin kx. So 2i sin kx divided by 2i. That is equal to sin kx. Okay. So now we have two relations. Cos kx is equal to e raised to ikx plus e raised to minus ikx divided by 2, and sin kx is equal to e raised to ikx minus e raised to minus ikx divided by 2i. Okay, so let me substitute this in our psi equation. Okay, so let this be equation number 1. Okay, this is our psi equation. So let this be equation number 2, and let this be equation number 1. Okay, because we will use this later. Okay, so I am going to substitute the value of cos kx and sin kx in equation number 2. So psi is equal to therefore psi is equal to a sin kx. What is sin kx? E raised to ikx minus e raised to minus kx divided by 2i. So I can write it like a divided by 2i. E raised to ikx minus e raised to minus ikx plus b cos kx, right? B cos kx. So I can write like b cos kx. Cos kx is equal to this one. Okay, so I can write it like b by 2 into e raised to ikx plus e raised to minus ikx. Okay, so now I can write like that is equal to a divided by 2i e raised to ikx e raised to ikx minus a divided by 2i, okay, e raised to minus ikx plus b by 2 into e raised to ikx plus b by 2 into e raised to minus ikx. Okay, now we have e raised to ikx and e raised to minus ikx terms. So let me put e raised to ikx terms together and e raised to minus ikx terms together. Okay, so e raised to ikx, this is e raised to ikx term, and this is also e raised to ikx term. So I can write like a divided by 2i plus, so not plus, yes, a divided by 2i plus b by 2, okay, e raised to ikx. Now I am going to put the e raised to minus ikx terms together. Okay, so I can put like plus e raised to minus ikx b by 2 minus a by 2i, a divided by 2i e raised to minus ikx. Okay, now let me put a by 2i plus b by 2 as another constant. Okay, as this is equal to c e raised to ikx plus b by 2 minus a by 2 is another constant, that is d e raised to minus ikx. Okay, so now I have another expression for psi. Okay, so this expression for psi is in another form. This is in the exponential form. So I have converted a trigonometric solution, or a solution in terms of the sine and cos in terms of the exponential functions. Okay, so let me call this as equation number 3. Okay, so after converting this sine function to this form, there are some benefits, and because it is easy to handle, and we can get some information about the wavelength easily from this function. Okay, so we will see how we can do this. So let me calculate what is the linear momentum associated with this particle. Why I am calculating linear momentum? Because once I know the linear momentum, I can get the wavelength, because we know the de Broglie relation, lambda is equal to h divided by p, or lambda is equal to Planck's constant divided by momentum. So once I know the momentum, then I can get it, or then I can calculate the lambda or wavelength associated with that particle. That is why I am going for momentum. So what is the momentum of this one? Momentum of this particle. Linear momentum of this particle. Linear momentum of this particle. Linear momentum. Okay. So if you want to get the linear momentum of the particle, you can construct an eigenvalue equation like a p cap psi is equal to p psi. Okay, where psi is an eigenfunction of p cap. So we can check whether this psi is an eigenfunction of p cap. Then only we can use this psi function in that form in the eigenvalue equation. Okay. So if you are checking, let me check it in the right side. Okay, I am just checking only. You don't need to write that in the examination if it is being asked. I am just working out to show you that whether this is an eigenfunction of the linear operator or not. But you know that linear operator px cap is equal to h divided by 2 pi I d by dx. This is a linear operator. Okay, you already know this. Okay, and I can check whether this I is an eigenfunction of this one. Okay, so if I want to check whether this is an eigenfunction, let me put that in the red color. Okay, so that you will understand that this is only a side work. Okay, px cap, maybe it is not very much visible to you. I will change to another color. Okay, px cap. Okay, px cap psi. I am going to evaluate px cap psi. That is equal to h divided by 2 pi I d by dx of psi, d by dx of psi. That is equal to h divided by 2 pi I d by dx of psi, means d by dx of c e raised to ix, c e raised to ikx plus d e raised to minus ikx. Okay, so that is equal to h divided by 2 pi I d by dx of this one, that is equal to c into e raised to ikx, d by dx of e raised to ikx, that is equal to ik into e raised to ikx plus d into minus ik into e raised to minus ikx. Okay, so that is equal to h divided by 2 pi. We have I as a ik as the a common factor here, right? So h by 2 pi I into ik into ik is taken as a common factor. So what is remaining there is c e raised to ikx minus d e raised to minus ikx. Okay, so I and I are cancelled. So what is remaining is hk divided by 2 pi into c e raised to ikx, c e raised to ikx minus d e raised to minus ikx. Okay, and now what is c e raised to ikx minus d e raised to minus ikx? That is not equal to psi. Psi is c e raised to ikx plus d e raised to ikx. So we cannot substitute psi here. If we could substitute psi here, then it would be in the form of px psi is equal to hk by 2 pi, means a constant multiplied by psi. But we cannot substitute psi here. So px cap psi is equal to hk divided by 2 pi into some other function. So it is not equal to hk by 2 pi into psi. So since this is not obeying the eigenvalue condition, psi is not an function of p cap. Okay, psi is not an eigenfunction of p cap. So I just to prove that we cannot simply use the psi function as an eigenfunction in an eigenvalue equation constructed by the linear momentum operator. That is not possible. Then what we can do? So actually we know that psi is a linear combination of two another functions, e raised to ikx and e raised to minus ikx, right? So this linear combination, okay, so psi is, even if psi is not an eigenfunction, psi is expressed as a linear combination of the eigenfunctions of h by 2 pi. If you check whether e raised to ikx is an eigenfunction of h by 2 pi, of course it is an eigenfunction of h by 2 pi I, because we have already done this in our previous classes. Because e raised to ikx is an eigenfunction of linear momentum operator, or e raised to minus ikx is also an eigenfunction of linear momentum operator. So these individual functions, okay, are eigenfunctions of the linear momentum operator. So what while learning the fourth postulate, we learned that if the psi function can be expressed as, or the wave function of a system can be expressed as, the linear combination of the eigenfunctions of some operator, okay, then each time when we are measuring that physical quantity, we will be getting the measure of that physical quantity as the eigenvalue of each eigenfunction. Okay, so in order to get the momentum, we don't need to operate the momentum operator with the psi function. Instead, we can operate the momentum of, we can operate the these functions c e raised to ikx or d e raised to ik minus ikx with the momentum operator. Okay, നമ്മൾ ഇതിനകത്ത് psi ഫംഗ്ഷനെ മൊമെന്റം ഓപ്പറേറ്റർ കൊണ്ട് ഓപ്പറേറ്റ് ചെയ്യുന്നതിൽ യാതൊരു അർത്ഥവുമില്ല. കാരണം psi എന്ന് പറയുന്നത് മൊമെന്റം ഓപ്പറേറ്ററിന്റെ ഐഗൻ ഫംഗ്ഷൻ അല്ല, പക്ഷേ ഇതൊരു ഐഗൻ ഫംഗ്ഷൻസിന്റെ സമ്മേഷൻ ആണ്, അല്ലെങ്കിൽ ഐഗൻ ഫംഗ്ഷൻസിന്റെ ലീനിയർ കോമ്പിനേഷൻ ആണ്. അതുകൊണ്ട് ഓരോ ഐഗൻ ഫംഗ്ഷനും എടുത്തുകൊണ്ട് നമുക്ക് എന്ത് ചെയ്യാം, ഇതിന്റെ മൊമെന്റം കണ്ടുപിടിക്കാം. ഓക്കെ, സോ നമ്മളിപ്പോൾ ആദ്യത്തെ ഐഗൻ ഫംഗ്ഷൻ എടുത്തുകൊണ്ട് മൊമെന്റം കണ്ടുപിടിക്കുമ്പോൾ നമുക്കൊരു പർട്ടിക്കുലർ ഐഗൻ വാല്യൂ കിട്ടും. രണ്ടാമത്തെ ഐഗൻ ഫംഗ്ഷൻ എടുത്ത് മൊമെന്റം കണ്ടുപിടിക്കുമ്പോൾ മറ്റൊരു ഐഗൻ വാല്യൂ കിട്ടും. ഓക്കെ, ഇറ്റ് മീൻസ് ദാറ്റ് വെൻ വി ആർ മെഷറിംഗ് ദ മൊമെന്റം of the system at different times, we may get the different eigenvalues. Okay, so നമ്മൾ അതാണ് ഇനി നോക്കാൻ പോകുന്നത്. So in order to get the momentum, linear momentum, we are taking only part of this psi function. For example, we can take a c e raised to ix. Okay, so what we will get when we are taking c e raised to ix, the linear momentum as eigenfunction of the linear momentum operator. So let us take this one. So linear momentum operator is here, and we can take the function as a c raised to ikx, and then let me construct the eigenvalue equation, that is px cap c raised to ikx. Okay, c raised to ikx is equal to h divided by 2 pi I d by dx of c e raised to I kx. Okay, so what is the result of this one? That is equal to h divided by 2 pi I into d by dx of this one, that is equal to c into ik into e raised to ikx, right? So I can write it like h into ik divided by 2 pi I into c e raised to ikx. So that is equal to kh divided by 2 pi c e raised to ikx. What is e raised to ikx? That is eigenfunction here, right? So that is c e raised to ikx. Okay, so we can write it like px cap z e raised to ikx is equal to kh divided by 2 pi c e raised to ikx. Okay, so what is this one? That is a momentum eigenvalue, and we are using momentum operator. So whatever we are getting here is the value of the momentum. So that is equal to kh divided by 2 pi. So momentum px is equal to kh divided by 2 pi. Now we can take another part of the wave function also in order to get the momentum. Okay, we can take this also. So this will also give the momentum value. So what will be the result if we are taking that as a eigenfunction? So if we are calculating the momentum with that one, we can construct the eigenvalue equation px cap d e raised to minus I kx, that is equal to h divided by 2 pi I d by dx of d e raised to minus I kx, okay, that is equal to h divided by 2 pi I into d into minus I k into e raised to minus I kx, minus I kx, okay. So I can write it like uh, h minus h I k divided by 2 pi I d e raised to minus I kx, or I can write like px cap into d e raised to minus I kx is equal to minus kh divided by 2 pi into d e raised to minus I kx, okay. So that is also an eigenvalue equation, right? So here we have the momentum operator. So whatever we are getting here is the momentum value. So from this one, we can get the value of momentum of the system Px is equal to minus kh divided by 2 pi. See, now we have got two momentum values. One is kh divided by 2 pi. Now we are getting minus kh divided by 2 pi. It means that when we are measuring the momentum of the system, we can either get kh by 2 pi, or when we are doing the same measurement another time, we may get the momentum as minus kh by 2 pi. Okay, in both cases, the modulus is same, or the value is same. The sign is different. It means that we are getting the first momentum when we are measuring, when the particle is moving in the plus x direction. So when the particle is in the plus direction, plus x direction, then the momentum px is equal to kh divided by 2 pi. And when the particle is moving in the minus x direction, then the momentum will be minus kh divided by 2 pi. Okay, so that is what we are getting. So it means that the average momentum of this particle will be 0, because it will be kh divided by 2 pi plus minus kh divided by 2 pi divided by 2, that is equal to 0. Practically, the average momentum will be 0. Now we have the momentum value px is equal to plus or minus kh divided by 2 pi, kh divided by 2 pi. And from this one, we can now calculate the lambda value. Okay, so lambda is equal to h divided by p from the de Broglie's relation. Okay, in your case, we denote it as dx. So we can write it like lambda is equal to h divided by what is px plus or minus kh divided by 2 pi, right? So plus or minus kh divided by 2 pi. So that is equal to 2 pi h divided by kh plus or minus 2 pi h divided by kh. That is equal to plus or minus 2 pi by k. Plus or minus 2 pi by k. Okay. Now, what is plus or minus 2 pi by k? Now I am going to our first equation. We had an equation here for k square. K square is equal to 8 pi square me by h square, right? So let me write it again here so that you can see it better. K square is equal to 8 pi square me divided by h square. Okay. So let me rearrange this one. So k square is equal to 4 pi square by h square. I am just rearranging this one. I am going to write like 4 pi square divided by h square into 2me. Okay, so that is equal to k square. So I can write it like so now I can write k is equal to root of this right hand side. So it is 2 pi by h into root of 2me, right? 2 pi by h into root of 2me. So I can write like 2 pi by 2 pi by k. Okay, 2 pi by k is equal to, from this one, 2 pi divided by k is equal to h divided by root of 2me, okay, h divided by root of 2me. So instead of 2 pi by k, I can write h divided by root of 2me. So I can write it here like plus or minus h divided by root of 2me. Okay, so the wavelength associated with the particle is equal to Planck's constant divided by root of 2me, where m is the mass of the particle and e is the energy of the particle. Okay, so it will have positive wavelength when it is moving in the x direction, and the wavelength will have negative sign when it is considered to be moving in the negative x direction. Okay, now you got an idea about the wavelength. Okay, now we can think about energy. Okay, energy of the system. Energy of the system. So what is the energy of the system? We can directly get the expression for the energy from the equation number 1. Okay, k square is equal to 8 pi square me by h square. So energy, for energy we can consider k square is equal to 8 pi square me divided by h square. Therefore, E is equal to k square h square divided by 8 pi square m. Okay, so here in this expression, k can have any value, so E can have also any value. So whatever value k is assuming, that will decide the value of E. Or in other words, there is no limit for the value of the energy of free particle. Or in other words, the energy of the free particle is not quantized. Okay, അതിന് പോസിബിൾ ആയിട്ടുള്ള എല്ലാ എനർജി സ്റ്റേറ്റിലും ഈ ഫ്രീ പാർട്ടിക്കിളിന് ഇരിക്കാനൊക്കും. എല്ലാ പോസിബിൾ എനർജി സ്റ്റേറ്റ്സും അത് പോസിബിൾ ആണ്. നമുക്ക് ഡയറക്റ്റ് ആയിട്ട് ഇങ്ങനെ ഒരു എക്സ്പ്രഷൻ കിട്ടും. ഇനി നിങ്ങൾക്ക് കൂടുതൽ നിങ്ങൾ ക്യൂരിയസ് ആണെന്നുണ്ടെങ്കിൽ വി ക്യാൻ ഗെറ്റ് ദ energy from the h cap psi is equal to E psi equation, because whenever we are getting energy, you may be thinking like, yeah, if you are using the energy operator, then we can get the energy, right? We can get the energy as an eigenvalue. If you are curious to get the energy in that way, you can get that. Okay, if you want to get it in that way, then you have to use the Hamiltonian operator. Okay, you will get the same result. Okay. Okay, I will show you how you can get the same result. Let us take the Hamiltonian operator. This is just for the curiosity. Okay, so let us take the Hamiltonian operator. Hamiltonian operator h cap is equal to minus h square divided by 8 pi square m d square by dx square plus v, but v is equal to 0 in our case. Okay, so that is a Hamiltonian. So we can construct the Schrodinger wave equation from this one. H cap psi is equal to E psi. H cap psi is equal to E psi. And after constructing the Schrodinger wave equation, okay, then we can get the value of E. So what we are going to do is we are going to calculate what is H cap psi, and then we will make it in the form of E psi, and from that one we will extract the value of psi. So let us calculate what is H cap psi. H cap psi is equal to minus h square divided by 8 pi square m. Okay, d square by dx square of psi. Okay, d square by dx square of psi, that is equal to minus h square divided by 8 pi square m d square by dx square of psi. What is psi? C e raised to ikx, c e raised to ikx plus d e raised to minus ikx. Okay, so that is the value of psi here. So let us now again simplify. That is equal to minus h square divided by 8 pi square m. Then d by dx of the first derivative of this one. Okay, that is equal to c ik e raised to ikx plus d minus ik e raised to minus ikx. Okay, so that is equal to minus h square divided by 8 pi square m of c ik into ik. Okay, so ik into ik e raised to ikx plus d into minus ik into minus ik e raised to minus ikx. Okay, so that is equal to minus h square divided by 8 pi square m. We have ik square and ik square. See, this is ik the whole square, and this is also ik the whole square, because this is minus ik into minus ik is equal to ik the whole square, right? So we have I square k square as the I square k square as a common factor here. So I can write it like I square k square into, what is in the bracket, c e raised to ikx plus d e raised to minus ikx. Okay, so we can write it like I square is equal to minus 1. So that minus 1 and this minus 1 will be multiplied together, and then it will be plus. So it is equal to h square divided by 8 pi square m into k square, okay, into c e raised to ikx plus d e raised to minus ikx minus ik, sorry, sometimes this writing become difficult, okay, minus ikx. So I can write it like h cap psi is equal to k square h square divided by 8 pi square m. What is c e raised to ikx plus d raised to minus ikx? That is equal to psi. So h cap psi is equal to a constant multiplied by psi. Therefore, this is the value of energy, right? H cap psi is equal to E psi. So this is E. Therefore, E is equal to k square h square divided by 8 pi square m. Okay. So we have obtained the same result here also. We had obtained this result here. E is equal to k square h square divided by 8 pi square m. And we can use the Schrodinger wave equation also in order to get the same equation. We just did this for the curiosity. Okay, we will get the same result. E is equal to k square h square divided by 8 pi square m. Now you have the idea about the energy of the particle, and also you know about the wavelength of the particle. Now you know that this particle actually has a two momentum value or two wavelength values, means in the sense that when it is moving in the plus x direction and when it is moving in the minus x direction. So let us move back to that discussion of the plus x, the movement in the plus x direction and movement in the minus x direction. So when it is moving in the plus x direction, it has a wavelength of plus h divided by root of 2me, and when it is moving in the minus x direction, it has a wavelength of minus h divided by root of 2me. Then what is the meaning of this one? Okay, now let us imagine that d is equal to 0. If d is equal to 0, then psi becomes c e raised to ikx, right? Because d is equal to 0. So when psi is equal to c e raised to ikx, then we have see, when psi is equal to c e raised to ikx, we have already done this one. When psi is equal to c e raised to ikx, we have a momentum value plus kh divided by 2 pi, and that corresponds to a wavelength value of h plus h divided by root of 2me. Okay, plus h divided by root of 2me, that we have done here. So when d is equal to 0, that corresponds to a wavelength. This corresponds to a wavelength which is equal to plus h divided by root of 2me. Okay, and if c is equal to 0, then psi is equal to d e raised to minus ikx, and that corresponds to a wavelength which is equal to minus h divided by root of 2me. It means that these are two extreme conditions. If this is the condition, if d is equal to 0, if this is the condition, means if this is the state of the system, then the particle is a wave in the positive x direction. And if this is the second one is the state of the system, then the particle is a wave in the minus x direction. And if you get any other value of c and d, okay, if any value of c and d, any other value of c and d, value of c and d, then the particle will be a superposition of both waves, means a superposition of wave in the x direction and superposition of wave in the minus x direction. Okay, that is the nature of this microscopic particle. So this microscopic particle in an extreme case can be a wave in the positive x direction, or in other words, in another extreme condition, it can be a wave in the minus x direction, and in the intermediate conditions or intermediate states, it can be a superposition of the waves in the plus x direction and minus x direction, and that's what we have to understand from here. And we have to again understand that this is a free particle. It can move from minus infinity to plus infinity. There is no boundary condition here, no boundary. It is not restricted. And in this type of a restricted particle, there is no limit for the energy, or the energy is not quantized. Okay, these are the things that we have to understand about this particle. Okay, so by applying quantum mechanics, we got some important idea of how what is the nature of a free particle in one dimension. I hope you enjoyed this lecture, and also I hope you are interested in the results and interpretations of the application of quantum mechanics for simple systems. Okay, and keep that interest on, and as I always say, keep writing, keep writing. That is the only way to learn quantum chemistry, and then you will be very much expert in writing in the steps in your examination. Okay, so thank you for watching, and stay tuned.